Thank you. Thank you, everybody, for coming and listening. Thank you to the Landscape Board for the invitation, and thank you, Ollie, for the introduction. So what is soil organic matter? Well, we used to measure it by setting it on fire and measuring what was left, weighing what was left. So that told us about soil organic matter. But it actually contains a heck of a lot more than just carbon. So carbon is about 65, 66% of it. You got oxygen and hydrogen just taking up space. Let's keep it together. And the important other bits, nitrogen, phosphorus, sulfur, other elements. So you can't manage carbon without managing nutrients. And these days, if you send a sample off to APAL or anywhere else, you are likely to get a number for carbon, not a number for organic matter, unless you ask it. So that's an important thing to understand, particularly if you're looking at data from other areas. I'll be presenting some data from the US that strangely is organic matter rather than organic carbon. I don't understand why, given the research group that did it, but there we are. Also important to understand this thing, carbonate, inorganic carbon. It is still carbon, but it's quite different, and we normally just completely ignore it in the context of organic matter. It doesn't form part of organic matter, though it can influence it. And I'm not really discussing that here today. So what can it do? Well, fertilizer is easy. You apply so many units of N, you expect to get a growth response. Apply a pesticide to manage a certain pest, you expect a response. Carbon, we've all said this morning, it's lovely, warm, fuzzy stuff. It makes us feel happy. But you can't prescriptively state exactly what it should do. There's probably more carbon in that lawn out there than there was in the soil we dug yesterday. Yet the soil we dug yesterday definitely seemed a lot more friable and a pleasanter place to be if you were a microbe. So what does it do? Well, I'm going to present quickly a couple of studies from the US. This, first of all, was a pot experiment that was done by Emily Oldfield, who has been a bit of a shining light in the US recently. She did a PhD a few years ago with Mark Bradford and others. It's a pot experiment, and they took a subsoil and surface soil and mixed the two together in different ratios to try and get a soil that was broadly similar but had different amounts of organic matter, to try and separate the two things. And the trouble is, whenever we try and do these things, if you change organic matter, you change everything else. So actually separating the impact of organic matter from everything else is quite difficult. What they found, and the figure isn't the clearest, but I will point and wave my arms around. You've got organic matter on the x-axis and above ground biomass on the y. The dotted lines are the experimental treatments of either nitrogen or irrigation, either half or full dose. And what you can see, Nashi mentioned this briefly, about a point at which organic matter sort of reaches the point where it's no longer helping you that much. And this is way over here, this is 8 to 9% organic matter, way higher than what we're talking about in most of our South Australian soils. Mostly we're down here. So organic matter is actually increasing yield in and of its own right. The nutrients and water are helping and have an interactive effect with it. But it's actually performing a function, been proven there, that it will increase yield in and of its own right, and it will be doing that through a number of different mechanisms. Resilience. Anybody want to hazard a guess at what I mean by that?
Resilience? Holding capacity?
Yes, but that could also be resistance. So resistance is basically there's a stress and it has no impact on you. Resilience is your ability to come back from that stress. And it's a different study out of the US, this time taking data from their equivalent of ABARES and looking at resilience of farming systems across a wide number of paddocks in the US. Quite a large number of paddocks. This is at county scale, over 12,000 county years, so 1 year, 1 county area per year. And they found that organic matter was increasing, there was an indicative link between organic matter and yield. So the same Totally different way of going about the study as the one I showed before, but again suggestive of the same thing. In good years, that was a nice trade-off. In the poor years, the soils that had higher organic matter had a much greater increase in yield. You had all these down here at low organic matter going up to the few that where they had built it really high. So that's one of the things that's harder to get your head around. You can say, you apply your fertilizer in that year, you expect a yield response. You don't tend to think about what might happen 2 or 3 years down the line. Organic matter is almost a question of looking at it the other way around. It's what wouldn't have happened if you'd had that organic matter, if you'd not had that organic matter there. They actually were able, because of the depth of the data, to postulate a couple of ways this was being done. So the organic matter itself was having a direct impact, but it was also having an impact via increasing cation exchange capacity, so exchange of nutrients, and also via its manipulation of water holding capacity. So it was having a direct effect, as shown in the previous study, and then also manipulating those 2 other aspects, and generally improving soil fertility. So where does it come from? We've had a lot of mention so far about the importance of growing things, net primary productivity, so that's the amount of carbon a plant fixes in the system after you account for its own losses from its own respiration, is absolute key. This can be modified by management. It's not fixed. Obviously, you can change your farm management. If you go from cropping to a mixed system, cropping pasture, you're almost certainly increasing NPP. But if you don't increase NPP, it is going to be very, very difficult to increase the amount of carbon you have in your soil. So I'm going to take a step sideways for a second. I try to be a bit straight down the line with this. I have written on regenerative agriculture. I think broadly it is a very, very sound thing to do. I also think broadly that most best practice Australian growers are doing something approaching it already and have been doing for a long period of time. And that's just something to bear in mind when listening to information from other countries where they may not have been. But these are the 5 main tenets. The one I want to linger on is this: the minimise chemical inputs. You're reducing fertiliser unless you're doing it carefully, and Colin touched on this, and he said reduce, not eliminate. Reduce excessive use, I think was your exact terminology. Yes, if you cut fertiliser out completely and carry on exporting nutrients, try doing that with money in your bank account and see what happens. So the first way to try and increase NPP, better growth. Overcoming soil constraints, I would say, needs to be done first. We talked about physical constraints. This is a study that Lynn MacDonald and Therese McBeath were working on the Sandy Soils project, looking at deep ripping and other deep amelioration aspects. Not for the faint-hearted, certainly shouldn't be done if you don't know what you're doing, because the downsides can definitely outweigh the positives. But where it was done right, they did manage to get a ton yield increase per year consistently for 4 years in one of the sites. They didn't in some of the other sites though. But it wouldn't have mattered how much fertiliser or whatever else they'd done. The primary constraint was compaction. The roots couldn't grow through it. You can make the rest of the soil as habitable as you want, but if the roots can't access all of it, you're not going to get anywhere. Other aspects that are equally important: disease and pest management, improved agronomy and improved varieties. So this is a little slide from Greg Rebetsky, who's been looking at long coleoptile varieties of wheat and canola to get better establishment in the first place. Something as simple as using the right variety in the right place at the right time goes a long way. We're talking about managing pretty large areas in most broad ecosystems. The easiest way to manage it, if you can, is to get the crop to do it for you. Cover crops. So we've looked at what we do with the crop that we're growing already. What if we grow something else? I work with Nashi, Mark Stanley, Jenny Stanton, Tom Robinson, and quite a few others on a project that ran across, well, quite a large area in southern Australia. That ran from 2018 to 2022, looking at cover crops, both mixed and single species, targeting summer where it could be done, grown short, sharp in the summer fallow and then terminated, but also in some places, particularly around the Mallee sites, they were grown in place of a winter cash crop. Because I don't have much time and I could give a talk that went on for 2 hours about this project alone, I'm going to summarise the findings. From dry sites to wet sites, This is a qualitative scale. If it's red, it was bad. If it was green, it was good. Average across all the sites across the bottom. Sorry, across all the variables across the bottom and across all the sites up the side. Various different measurements in there. Soil moisture content went down, not surprising. Soil nitrate went down, also not surprising. Organic nitrogen, microbial nitrogen, rates of nitrogen turnover went up, and they were the most consistent findings of all. So basically you're taking that lossy nitrogen pool, nitrate, and turning it into something that in most cases is relatively easily available, just not available like that. So it should be being released at more or less the rate the crop wants it, rather than being at risk of too much loss. Other things, clearly cover crop biomass was mostly higher in sites where we grew cover crops, not always. In the context of summer weed control, our control treatment there was business as usual. So if you had a grower who wasn't particularly careful about making sure that they killed everything, they didn't do that in the experiments either. And that's important to note as well, that weeds do still perform a biological function. They can be trouble to manage in other ways, but it's still a living plant, still doing stuff. Clearly that wasn't a pristine lawn out there. The plantain's doing just as much as the grass. Yield. In some cases, look, yield did go down. It's almost certainly a moisture hit when you're talking about trying to grow these things in summer. And it's worth bearing in mind that if you do this badly, not only will the cover crop chew up some of the water and not perform particularly well, it then takes some of the water that might have got you over a pretty hard year in your cash crop as well. Neither plant does particularly well, and you get less inputs from the plant as a result. So it's one of these things, particularly in our dry environments, that needs to be done carefully. Water holding capacity changed a little bit in some places and generally in the wetter areas, which is useful. Soil organic carbon, I'm highlighting Jenny's site here at Streaky Bay. Stokes Bay, sorry Jenny, yes. Streaky's up there somewhere. We actually had a statistically significant increase in soil carbon as a result of the cover crops at that site. And in most of the studies, although we had a 4-year project, in most places we only had 1 or 2 years of the cover crop being in, rather than trying to force growers to grow them in years that it just simply wasn't possible. We basically said, treat this as you would adopt it if you were trying, rather than because this is a project you must do it. Also, if you do want to measure effect of a treatment, turns out fungal diversity is probably one of the most useful of all to tell you there is a difference. I'm going to have to be very, very quick. All right. Nitrogen. I mentioned nutrients before. I'm going to fly through this first set of slides. This is data from Rob Norton's study for GRDC a few years ago across 125 different sites across Eastern Australia. Almost every single one of them was exporting more nitrogen than it brings in. So that nitrogen has to come from somewhere. And I want to emphasize this study here. This is a study out of the US that is a cause of a lot of misunderstanding. It's a long-term experiment where they looked at adding nutrients versus the control. Nutrients changed from being manure in the 60s to urea, and they saw a big decrease. And what they said was applying mineral nitrogen was causing a decrease in carbon. Not quite. What is actually causing that decrease is simply the fact you're not applying 4 or 5 tons per hectare of organic matter every year. So the fertilizer is still providing nutrition for the crop just can't provide as much carbon as you were bringing in from somewhere else. You were bringing in carbon above and beyond what MPP is providing. And this has caused a lot of misunderstanding that really is important to be clear about. And this is quite a useful perspective piece that came out of the US and other places recently. This point here of being points at which you get the right amount of nitrogen. If you're below it, you're increasing organic carbon, etc. Neutral or negative effect of nitrogen application on soil organic carbon does happen when you're applying too much. Roots don't put as much effort into growing where they need to be. There are losses of nitrogen that can happen. But at least when considering organic matter alone and not other losses, and clearly applying too much nitrogen is not a good thing to be doing, it isn't the nitrogen itself that's causing you to burn off carbon. Since we've talked about fertiliser, I will flash up the James Hunt's EnBank work, again focusing on over a longer term period, looking at where the offsets are for nitrogen application. And in actual fact, the benefits you get from having the nitrogen there in an unexpected good year, generally at least economically, outweigh the losses of not having enough in a poor year. But I don't work for a fertiliser company. I work for CSIRO, and I'm quite keen to find other ways that are not quite as industrious to build nitrogen. This is data that astonished me when I saw it. Rowan Brill, an agronomist who most people in the room would know, did this with GRDC over the last couple of years. I think the trials are still running at the moment. These numbers are quite spectacular. It's total biomass of various different legume crops, an amount of N fixed. Up here, some crazy faba beans in a very, very good year. This is atypical. Don't take this as this will happen. 600 units of N fixed. After harvest, still around about 300 units of N remaining. Those were really big faba bean crops. You're not going to get that out of lentils. Lentils are down here. But it does dispel the myth of the idea that if you have a legume, a grain legume, you're not necessarily taking all the N away. It's not going to behave the same way as Medic would, but at the same time, clearly if you get the year and variety right, the numbers can be substantial. Key thing to bear in mind is that if you stop doing something that was building carbon, it doesn't stay. The microbes are still there, the microbes are still active. This is long-term data from Rothamsted, and this is where they stopped applying manure. Looks fairly similar to the study in the US where they stopped applying manure but carried on applying nitrogen. It wasn't the nitrogen causing the problem, it's the fact they stopped applying the extra carbon. And it's the microbes that do both things. They have to to live, they turn it over. They build more carbon, they release some nutrients, but some will get lost. So every bit of input that goes into a microbe, some of it ends up here as CO2. And what you're trying to do is make sure that this arrow allows for enough to go down here so that you don't keep burning it off over time. That's why long fallows are not great either. So to wrap up, water availability limits yield, we know that. Moisture preservation and conservative N application in Australian broadacre systems. There's a strong rationale as to why, but it is definitely starting to bite in the context of organic matter is feeding your crops, which is good, but you need to feed the organic matter, and you do that through feeding the crop as well. In our broadacre systems, ultimately you are limited by NPP. Our grassy annual crops do not put as much carbon below ground as pastures do. It's a simple fact of their life strategies. So you have to understand that there are limits to what can be achieved, but we can definitely improve in some cases. And if you're typically focusing at improving NPP, not necessarily yield, but NPP overall, that will get you a good long way forward. So with that, thank you for your time. Thank most of the people who generate the data or help me in many ways, funders, and happy to take any questions at the end.
Thank you, Mark.